Right, so the quiz is there. Oh, I haven't checked. Did anyone do it? I can easily find it. Last time I checked, no one had done it. Oh, looky! Oh, someone got it wrong. Tusk. 2 people have done it. Only, oh, if you don't care, it's cheap marks.
Because there is no carrot.
There is a carrot, it's worth marks. You're saying you leave it to the last minute, yeah. Alright, fine. We have to learn to live without carrots.
Or you can give us bonus marks for the quiz too.
I could give you what?
You can give out bonus marks for the quiz.
No. What? Oh. For the people who've done it early. In fact, there's a list in order of time, maybe. No. Because I didn't tell you up front. Alright, assignment's out. No lectures next week, hooray! And why is it hooray? Because I'm not here. I'm gone and Jashank didn't want to take the lectures.
What about the content that would normally be covered next week?
Yeah, no, I mean I'm working to the 3-term, 10-week timetable.
Right.
So we just skip week 5 and then we still got 7 weeks in which to cover another 6 weeks worth of material. So it fits, it's no problem. We just finish a week later than what I'd planned. In fact, the way CSE is structuring all its courses, it's going to be 2 plus 2, like this course, two lectures a week, 2 hours, over 9 weeks. Which means you can have a break somewhere in the middle. So that's up to the lecturer to decide when that break is. So I've arbitrarily decided week 5. Now, of course, we've still got mid-semester for one last time, so you're not going to get mid-semester breaks from now on. If you're still around, maybe you're finishing this semester, so you don't care about terms. But if you're going to be here next year, 10-week terms. But at least only 3 courses per term. Anyway, so no lectures next week. Don't turn up here, otherwise you'll be by yourself and wondering, why isn't anyone else here? Right, so today I want to talk more about scanning a little bit, sorting, projection, and start work on implementing selection. Right, here's another famous database person. Who? First question, when I first looked at this picture, I was thinking, boy or girl? It's actually a woman, because it's about time I had a famous database woman, and her name is Laura Huss, so that's a little bit more obvious. So she went to Uni of Texas, and since then has been living the luxury life at IBM research labs in Silly Valley, and she's director of something called the Accelerated Discovery Lab, whatever that means. I assume it's some kind of data analytics thing. So she's very well known for her research in information integration, which is basically take information from a whole bunch of sources, not necessarily structured sources, and try and put them into a form where they can be used as a single database. And federated database is basically where you've got a whole lot of sources that are structured already, so they're in database form, and you want to try and use them as a single database. So the standard way of doing that is to come up, so they've all got information, presumably they all have information that's vaguely related. So come up with some sort of schema sitting over the top of all the databases, and then some way of mapping the individual database schemas into the global schema. And schema equivalence, schema mapping is an interesting database problem that, as far as I can tell, still isn't nicely solved. But she's had a go at some of the stuff like this. So her earlier work was on extensible databases, so a little bit like Postgres, but trying to explore all sorts of different kinds of data. Then a couple of federated databases, and some more recent work is on schema mapping. So pretty well known. Not as well known. Oh, maybe she is as well known as Jeffrey Woolman. I don't know. All right, let's hope. Now, getting back to this debacle. The reason I couldn't work out how we knew whether the transactions were finished or not is because there's an extra little bit of information in each tuple. So xmin and xmax tell us, or xmin certainly tells us which transaction created the tuple. Now the question is whether that transaction has committed, and the way we know that is we look inside this mask. So there's a bit in there that says the transaction that created the tuple has committed. So therefore the tuple definitely exists. Yeah, so that was the trick for working out whether that tuple really exists or not. If you want to take a look at the visibility checks, and this is quite interesting because these visibility checks have to be done every time we're thinking about accessing a tuple. Does a tuple, is that really visible to me? You know, was it created long enough ago that the transaction is committed, and therefore I'm allowed to look at it? So I thought I wouldn't deal with MIPS assembler. That was the previous lecture. Let's get rid of that. Oh, there's still one. Oh God. Help. I don't care. Let's just put that away and get up the other one. Now I have to guess. Could be that one. Ha, good guess. Alright. So let me see. Yes, down here. Okay. So one interesting notion that Postgres has the notion of a snapshot, which kind of gives a little window on what transactions have completed and so on, which is helpful in working out visibility stuff. But the magical place where it's all tested is in here. So tuple qualifier or whatever, does this tuple qualify to be worth looking at or something? Oh, and I was already looking at it. What do you know? So there's a nice blurb at the start which describes things quite nicely, and then you get down to, and there's various flavours of checking whether a tuple is visible or not. And finally we get to, these are the hint bits that tell you whether among other things, whether transactions are completed or not. And then let's randomly, oh no, I know what I wanted. Here, tuple since we were talking about multi-version concurrency control. Alright, so is this tuple visible under MVCC? So there's a snapshot involved which tells you about recently active transactions, I guess. Information about a tuple, information about transactions, and I didn't check what the buffer was. Don't know. But in any case, the reason I wanted to show you this was, this is what it has to do to work out whether a tuple is visible or not. It's a lot of code. And still we go, and things like, okay, xmin is committed, but maybe not according to the snapshot. So concurrency blows out the size. Oh, there we are, finally reached the end. Blows out the size of all this code significantly. If we didn't have to deal with concurrency, then I can tell you that thing would be a hell of a lot smaller. And there's other things like if there's a vacuum running at the moment, it has this tuple being sucked away by the vacuum, etc., etc. So there's a lot of work to be done just to work out whether a tuple is visible or not. Quite interesting. A lot of that, the information that's needed to do that is in buffers, so at least we don't have to go and read it. And maybe you only execute one branch of the if, so it doesn't end up taking that long. But it's quite complex. You can go and have a look at it if you want to do training. Alright, so talking about scanning, we were talking about scanning last time, and there's some kind of data structure that keeps track of the state of the scan. You initialize it by saying, hey, I want to look at this relation, and I think keys, if I remember correctly, is a list, it's a representation of the where clause, effectively. So if you're doing a scan and you're interested in only tuples that satisfy a certain condition, like the value of the age field is greater than 40, then there'd be a representation for that test in here. And so that stuff all gets put into the begin scan. Then we've got get the next tuple. And you can go in both directions, go forward through the file or backward through the file. And by the way, this is all dealing with heap files, which are just arbitrary collection of pages with tuples dumped in wherever they fit, basically. Something to clean up afterwards, and checking whether the tuple satisfies the test that you were looking for. So the tup is the data from the tuple, desk is the description of the schema of the table, and keys is the set of conditions, so it's probably the set of conditions that need to be checked. So once again, a fair bit of work as you're scanning to work out whether you want a particular tuple. And it's got the kind of stuff you'd expect, a snapshot of what the state of all the transactions that were when the scan started, which determines what tuples are visible, the conditions that determine whether you're interested in a tuple. Once you work out that it's visible, information about the relation, then the size of the number of pages that you need to scan, and then currency information, so what's the current tuple, what's the current page, and so on. So all those examples were for heap files. Heap files might be just arbitrary lumps of tuples chucked into blocks. Possibly, even if that's what they look like, there still might be an index associated with it to make certain kinds of queries go faster, but we're not assuming there's any hashing going on. That's a separate type of file. And there's various file structures in Postgres, but each of them has to implement a collection of operations with something like these. Okay, and you see this kind of structure when you're implementing the new data type. You see that similar kind of thing. Every data type has to have certain kinds of operations, like reading in a constant value of the type, writing it out, and so on. Equality test. All right. So let's get on to some relational operators. So this is the kind of level that we're operating at now. We've moved up from the bottom. So this is a bottom-up exploration of databases. Right, so far we've looked at scanning, which is a really simple kind of relational operation, if you want to put it like that. Looked at various kinds of file structures. So now what we want to look at are some more interesting operations and some different kinds of file structures to make these operations run faster, in particular selection. Right, so once again, a file consists of a sequence of blocks, B blocks, where each block contains records, and potentially overflow blocks. If, for example, if we're talking about a hash file, if we fill up that bucket and we need to have more space in the bucket, we can allocate overflow blocks, typically in a separate file, and certainly that's true in the case of Postgres. When we're talking about cost analysis, I've abandoned talking about the time to read and the time to write, so we're really going to just analyse things in terms of the number of page accesses. Generally, that's just number of pages read. For updates, we have to distinguish. We read a lot of pages, we might not write a lot, because we read a page, we discover there's no tuples on it that need to be updated, so we don't have to write it out again. Since any query that we ask, we can look at different ways of solving it. Hopefully, whatever method we choose to solve it is going to produce the same answer, and so the output is going to be the same, so we don't need to worry about the cost of writing the output. And we're assuming there's just enough buffers for whatever method we're using, so every request causes a read, every release causes a write if the page has been modified. So in some sense we're looking at a worst case scenario. Obviously the buffering is going to help, but it's going to help in unpredictable ways depending on what other transactions are using, what relations, and if they're using the same relations as us, and they happen to have left some of them in the buffer pool, and so on. Alright, sorting. Sorting appears explicitly in SQL using order by. It's also used internally by a number of other operations. So as we'll see soon, how do we deal with duplicate tuples in implementing projection if we are to select distinct, and sorting is involved certainly in Postgres in doing that. Ordering files to make selection more efficient. We're not necessarily going to store files in sorted order. It makes insertion more expensive and potentially update as well. Sorting is used internally in various flavors of join, and also it can be used to form tuple groups for group by operations. So as soon as you say sorting, people think of things like quick sort, bubble sort. Not sure why you would, but you might. Quick sort and merge sort that we talk about in data structures courses. They're not designed for sorting large amounts of data unless you have a very large memory to do the sort in. They're really designed for stuff loaded into data. So when you're talking about sorting on disks, it's always merge sort. So it's a very simple example of merge sort. We've got a whole bunch of pages, each page having up to 2 tuples in it. So initially the file's totally unordered. First time through we read each page and we do a sort within the page. So we sort the tuples in each page. And hopefully they're all sorted. In the next pass we take a pair of pages and we use a merging operation to make sure that across both of those pages everything is sorted. So you can see same thing's happened here, same thing here. Sometimes you end up with pages that are by themselves and have less than the full complement of tuples, but it still works fine. Alright, in the next pass we take the tuples that are of length 2 and we merge them to become tuples of length 4. And then we take another pass where we take the runs of length 4 and we merge them to be runs of length 8, and if that happens to be, like it is in this case, the entire file, then everything's sorted and we're done. So the merge step, let's say we take these 2 runs down here, we're going to load up the first page from each of the runs and we're going to look at the first tuple in each page in order and pick the one with the lowest key value. So these values here are key values and we're sorting based on this key. So for the sake of argument we might choose that one, so we can stick that there. Then we'll advance to the next tuple here and the next tuple here. Well, we're still at 1, so that's going to be smaller. That'll get pushed here. Then we'll get the 2s, then we'll get the 3s, the 4s, and so on. And ultimately the whole thing is sorted. Now you can do all that with just 3 buffers. So you need 2 input buffers, 1 output buffer, regardless of how long the runs are, because you're always looking at just one, the current page in each of the runs. So there's an assumption here, that's the assumption that we're using on everything, that the cost of doing this merge between these 2 pages in memory is almost nothing, and the real cost is having to read the pages in each time. So if we're going to do this, we need some kind of comparison function, so we know which is the smaller of the current pair of tuples. So somewhere in the system there's going to be a tuple comparison operation, and if you know C, well, you must know C, otherwise you shouldn't be doing this course. You're going to struggle with assignment 1 and assignment 2 and the exam. So C's got a function string compare, which returns, in fact, less than 0 if the first tuple is less than the second tuple, or the second string. Greater than 0, not necessarily 1 or minus 1, and 0 if the 2 strings are equal. So we can have a similar kind of operation here. So R1 and R2 are tuples, F is a field, and we assume that we can extract the value of a field from a tuple by doing that. I think in some previous slides I had some function get field or something like that. So that's what you'd apply here. So you get the field from the 2 tuples, check whether the field value in the first tuple is less than the field value in the second tuple. If it is, you return -1, otherwise you return 1, otherwise you return 0. So this is just doing a comparison, and that's going to be used by whatever process is driving the sort. And of course, since attribute values can be of any type, then we're assuming that that this isn't just the less than for int values, that there's some less than that works on any kind of type, like dates and sets and so on. So that's a very simple case, but in reality, what we're normally dealing with in an order by is a number of attributes, and maybe the order is reversed for some of those attributes. So here we're ordering by descending age, so we start with the oldest students, and then we sort in ascending order on the year enrolled. So what that's going to give us, the oldest student first, and the oldest student who enrolled first, and so on all the way down. So how do we represent that? Well, we have to have a list of the ordering criteria. So there's going to be one entry in this list for each of the fields that we're sorting on. So there'll be some entry for age, if we're talking about this example here, which also contains information to say that it's descending, and there'll be another entry in the criteria that says we're sorting in ascending order on the year enrolled. So doing a multi-attribute sorting function like that is relatively straightforward. We simply iterate through all the criteria until we find one where there's a difference, and we'll just keep going while there is no difference. And if there's no difference all the way through, then the tuples must be equal according to the sorting criteria, and then we can just, we return 0 to indicate that. Otherwise, if we find that a particular pair of attributes are sorted in a certain ordered in a certain way, then we return the appropriate value. Oh yeah, I did get it right. Tricked myself by changing the order of the operators. So if it's ascending order, then we do what we had on the previous slide. If it's descending order, we do the converse of that. So it's not too difficult to envisage how you might implement a sort of generic tuple comparison thing. Alright, so 2A merge sort, how much does it cost? Well, how many passes do we have to do? We have to do log 2b passes, because each time we double the length of the runs, and after log 2b times, then we'll have covered the entire file. I'm just thinking whether I've counted in that the first pass where we sorted within the pages. So maybe it's log 2b plus 1, ceiling of log 2b plus 1. Anyway, that becomes more explicit later on. So every time we do a pass through the file, clearly we're reading the entire file, but we're looking at different bits of it, but every page gets read, and also every page gets written. So the total cost is the number of times we have to make a pass across the file, 2, 1 read, 1 write for each page, and that's total number of pages. So if you've got a relation like this, and we're doing two-way sorting, we've got to read and write the entire file 11 times, which is not great if the file's a gigabyte long or something like that. So can we do better? And yes, the answer is straightforward. We have n-way merge sort. So pretty much every operation can be improved by throwing more buffers at it. So in this case, we throw more input buffers at it. So in the previous example, we had 2 input buffers, and we're merging 2 runs, or a pair of runs each time. Now we're merging n runs at a time. We could have multiple output buffers, and one reason why you might do that, one fills up, you start writing it, and you can keep going, reading and doing merging into the other buffer. So you don't need that, you can get by with just a single buffer. So n plus 1 buffers. So yeah, typically we're only dealing with 1 output buffer. So here's how it might work. So one thing we can do is we can have a first pass through the memory where we read every page in the relation, and we use all of the buffers, and we read 1 page into each buffer and sort all the tuples and then write the page out. So we can sort B pages at a time. If the file's longer than B pages, then we read 1 chunk of B pages, eventually sort them all, write them out. Then we read another chunk of B pages, sort them, write them out. We're not necessarily doing any merging at this stage, we're just sorting within the page, and we can use a in-memory sort like quick sort or something to do that. So what we end up with after the first pass through the file, every page is sorted internally. Now one way of looking at that is we've got a sorted run of length 1, okay, 1 page. And then we'll do an n-way merge, and we'll take the first n pages and merge them together, and that'll give us a sorted run of length n. Then we'll take the next n pages, that'll give us a sorted run of length n, and so on. So that gives us runs of length multiplied by n each time. So how many times do we have to do that? This is going to be log n rather than log 2. So what else is interesting here? So we know the number of runs that are required. So each time we're sorting n runs because we've got n input buffers, and so it's the next n pages from the input file. After that first pass, each individual page is sorted, then we get n sorted pages, we run the merge operation on them, and we have a sorted run of length n pages where all of the tuples within those n pages are sorted. And we do that enough times and we eventually end up with the whole thing being sorted. So the merging function for merging n runs, basically you've got n pages, you look for all sorting buffers, you look for the buffer that contains the smallest current tuple. So every page is a current tuple which gradually moves through the page. We find the buffer of the smallest current tuple, check whether the output buffer's full. This is the standard buffering that goes on. So we're going to read tuples from a page, stick them in an output buffer, eventually it fills up, so we write it out, and then we clear it out and keep going. And so copy the current tuple to the output buffer, go to the next tuple in that particular buffer, and if there is no next tuple, it means we've just cleaned out that buffer, So we get another page to put in there. Oh, sorry, if there's no more tuples, we check whether there are any pages left in the current run. If there aren't, then we say, all right, forget about that run and just look at n-1 runs that still have tuples in them, and we just keep going like that, picking the smallest tuple from the remaining buffers, writing it to the output buffer, and so on. And if we get to the end and we've got the output buffer's still got stuff in it, then we have to obviously write that out as well. Right, so what about the cost for that? So if we've got 4,096 blocks, and let's say we've got 16 buffers, so in the first pass we can use all 16 buffers to read in a chunk of 16 pages and individually sort the pages. Now, maybe, since we've got 16 pages in memory, maybe we can come up with some clever way of sorting the entire 16 pages, which would save a bit of time, but let's just assume that we can sort each individual page. So that's going to give us 256 runs. Each run is 16 pages long. Now we switch, on pass 1, we switch to having 15 input buffers and 1 output buffer. And so that allows us to have 240 page runs, so 16 times 15. Each of these 16 page runs gets merged with 15 others, and so we have that many runs. On the next pass, 3,600 page runs, so they're quite long, and you can see there's only 4 passes, and this is quite a large file. I think, how does it compare to the previous one, or is it the same size? No, it's totally different. In any case, 4,096 pages, which is bigger than the previous file. It's only 4 passes to completely sort it. And in fact, the 2A merge sort might even need more than 11 passes to do that. Alright, so the first pass reads B pages and writes out B pages, giving us that many runs. Oh, so we are assuming that we're going to sort the B pages that we've read. And then the remaining passes is that each time. So we've got the starting number of runs is that, and then log in more passes to complete the sort. So every pass, regardless of how long the runs are or whatever, always reads in B pages and writes out B pages. Now we're kind of making an assumption here that all of the pages are full. If it turned out that the pages weren't full, maybe in this first pass we could even do a little bit of compression, and the number of pages that got written out mightn't be equal to B, it might be less than B. But let's assume all the pages are full. That's kind of the worst case scenario. So that'll be the total cost. So the 2 is the fact that we're reading and writing. The B is the number of pages. So read B pages, write B pages. The 1 is the first pass, and then that's the number of subsequent passes that we need to sort the entire file.
Excuse me, Professor.
Yep.
In the pass 1 and pass 2,
Yep.
pages is more than 4,096. So can you explain?
Oh, is it?
why?
Yeah, I guess, how much more is it? Ooh.
4,300.
For the pass 1 is 4,320.
And the original file is, now how long are the runs? I might have allowed for a complete run at the end that's not full. Would that make sense? Nope. In that case, I stuffed up my calculations. So the run's are definitely going to be 240 pages long, 15 input buffers, 16 pages in each run. Alright, let's go here. Sorry, what was it? Oh yeah, 4096 divided by 240. 17 and a tiny little bit. So, yeah, alright, so I might have over-egged the omelette and made all the runs the same length. So there's going to be 18 runs, and the run at the end is very short. And you're right, we wouldn't normally write that out. I don't think that affects the number. In fact, it would affect the calculation if we actually wrote all of those runs out, including the very short run at the end. If we wrote all the pages, then we'd be writing more than B pages each time. So, yeah, and we can't avoid the fact that there are 18 runs in any case. So I think that's all right. So conceptually we have 18 runs. Most of the runs are 240 pages, but there could be one at the end that's shorter than that. Alright, so let's have a look at another example where this time we've got to sort of go from scratch. So if I grab all that information, I'll just do it. Oh, in fact, I'll grab more than that. I'll grab all of that. In fact, I want to use it. Ha! All right. Okay, so first thing we've got to work out how many tuples per page, and then that's going to tell us how many pages we need. I'm not sure where H and D came from. Was there anything on the question? Oh yeah, good. I thought there wasn't any mention of the header and the presence bit. Okay, so this relates back to the example we had last time, where a page contains tuple data, but it also contains a directory, typically. No, in this case, all right, all the tuples are the same size. So we've got some header data, we don't know what that is, and we've also got a bit vector that tells us which slots are actually used and which slots aren't. So if we take all that into consideration, we end up with 64 tuples per page. All right. Oh yeah, so the number of pages, which is what we're trying to work out, is 3,968. Is that right? This is what happens when you don't check your exercises before you come into the lecture. Right, so I suspect this doesn't quite fill up the last page, but we still don't have the whole page there. So in theory, that's the amount of tuples we can have. Yeah, so there's 24 wasted bytes. Oh no, this is within a page. Duh. All right, so 64 tuples in a page. Oh, this is just to demonstrate that it actually is consistent with all of that. All right, so we had a certain number of tuples, so that's the number of pages. What a coincidence, works out to 16k. All right, 9 total buffers, input buffers 8. So the first pass, we read in 9 pages at a time, and we do a complete sort of those pages because they're all in memory, and in theory we can shuffle tuples around as we like. Here I guess we're assuming that we're not dealing with a hash file or something like that, or certainly the thing we get at the end isn't going to be a hashed file. So that's the size of the runs after the first pass. Read your 9 pages, sort them, write them out. Then after that, we take in our 9-page runs, and we've got 8 input buffers, 1 output buffer. So that's the size of the runs after the second pass and after the third pass, and 5 passes over the file. That's the number of pages. That's a lot of pages, to the 14, okay. And 5 passes. Each pass reads and writes the entire file, and that's the number of pages in the file. So that's a fairly big number. Can we do better if we have more buffers? Let's just jump to the bottom line. Yes, there's less passes, still a lot of writing, and if we chuck even more buffers at it, we can have 1 less pass. And if we chucked even more buffers, we could read the entire file into memory and sort it all in memory and then write it out. And there'd be only 1 pass, which would amount to that. All right. Right, so that's the general idea of in-way merge sort. So what does Postgres do? Strangely, it's got a directory called sort inside the backend stuff, and there's a file called tuple sort. So first thing that happens is tuples, we don't actually sort entire tuples. We sort things that are just a pointer to the original tuple and the key and the attribute that we're actually sorting on. Now, if we're sorting on multiple attributes, we'd have to have a copy of each attribute loaded, but if we're just sorting on one attribute, then all we got to do is, as we scan so the analysis is going to end up being different, but we scan the file the first time, we read each tuple, we grab the attribute that we're sorting on, and we stick that in a sort of pseudo tuple which contains that key plus the OID, if you like, of the original tuple. So much smaller, so clearly we're going to end up with less pages in the subsequent passes through the file. Of course, at the end we've got to go, if we really want to sort the actual file, then we've got to go through and reconcile the sorted keys with the actual tuples, which is an interesting thought. Alright, so don't need to look at the actual tuples during the sort, unless we happen to have multiple attributes, in which case maybe we do. If, having done this, we discover that everything will fit into memory, then Postgres just uses quicksort. Good idea. If the memory fills up while we're doing this, then we've got to go back to the in-way merging. And in the process of reading in and extracting these tuple pointers and keys, we can do a bit of sorting. So the disk-based sort has similar kind of structure to what we were just talking about. How many buffers do they use? As many as they can grab. And if you go and look at the code, it's all described in terms of tapes. So it's like you're loading up a tape, reading the tuples off the tape, writing them to another tape, rewinding, reading from the tape again, and so on, which is quite interesting. That kind of harks back to, in the storage manager, there's an assumption that we've got all these different kinds of devices, not just disks, but we could have tape devices as well, although I suspect never again. As far as these generic sorting functions, the thing I call tuple compare, This is what Postgres has. Let me see. One thing that you have to take into account is whether you want, and this is something Postgres allows, I don't know about other databases, but tuples with nulls in the sort key, where do they go? So you can either arbitrarily put them at the start or put them at the end, and Postgres lets you specify how you want to do it. So that information gets put in there. A sorting function. So once again, we've got OIDs, which are references to catalogue tables, and we can go and get all of the relevant information via the catalogue tables. And then when you want to apply the sort function, this is more like the tup compare function. So you've got two tuples, or the data from two tuples. Is the sort key in this case null? So we've got to check for both things. Sort flags, among other things, would include whether it's ascending, descending, and finally the function that actually compares the two values depending on the type of the attribute. Alright, and since it's 5 o'clock, let's stop there. And there's a new topic.